Hey, hi everyone. Good morning. Parkavi, is it you?
Yeah, hello, Santin.
Hi, Dinesh.
How are you? I was in leave on yesterday.
I'm good. Everything is good. I hope everything is fine at your end as well.
Yeah,
Parkavi or Gracie, whosoever it is. Yeah, thank you. Okay, just give me a moment. All right. Okay, we'll start in just a minute. Or maybe let's wait for 2 more minutes. At least other people would join and then. Okay.
sure, Santin.
All right. So we have almost completed your syllabus. So I just wanted to see like if there is anything pending. So you guys could let me know, and probably we'll finish it today or tomorrow. Okay. All right. So I started from this module 14. Okay. So is there anything which is remaining here?
No, Santin, that.
Others can also probably contribute to it. So Rajesh is also there. Maybe let's wait for maybe 3 more minutes. Okay. So let others also join in. I just want to ensure that like if every topic that we have seen is covered or not. Okay. From the syllabus. So this is what Guvi provided me for your syllabus, and we have to end here. End here. Like from my side, it is almost done. I'll probably cover a few more topics which are important, which probably are not here. Okay, let's wait for others to join in. So we'll start when at least say 3 to 4 participants are there. Currently, there are two. So probably today or tomorrow will be my last class with you guys. Okay. Depending on how much I'm able to cover today.
Sure, Santin.
Meanwhile, if you guys have any questions, we can discuss those. Any questions as such? It could be from any topic. Okay, after this, you only have your case studies. Maybe 2 more minutes. If nobody shows up, then I'll start.
Sure. And we also got a third project signing, the Biscard.
Which one?
The Biscard extraction. They'll give us a business card and we have to.
Oh, okay. All right. I've heard of it. I mean, I'm not a part of the project mentoring team, but I've heard of that project. Basically, you have to extract info
Yes.
from business cards using an OCR. And then you have to store it maybe in some kind of a database, could be a vector database or NoSQL or maybe SQL database. And I think you have to create a web app or maybe a deployment service that you can use to, display the content or fetch the, use SQL to or NoSQL to fetch the content from your database and display it.
Yeah, with the easy OCR, they said, actually yesterday when we had seen that project, what
Okay.
is all about, so I need to dig in. Actually, you know what the fun fact is, like on Saturday or something, Monday, I've completed the phone pay project.
Mhm.
While I'm sending an email that, okay, I'm completed the project, I'm receiving an email that you have been assigned an another customer. I was like, give me some time. But I'm in a completion phase, right? So that I thought of, because for completing this project itself, I've taken leave and all this in my company. But yeah,
I think this is necessary from their side also.
that is totally I can understand, and I'm learning a lot of things also.
Okay, let's start. I don't think many people will join today. Okay, just a moment. If Rajesh, are you there, by the way? Can you speak up for a minute or two?
Yes, Anton, yeah.
So Rajesh, if you remember, I think you also attended most of my classes. So if you could tell me, like, if there is anything pending from this. Any topic that you see we haven't covered though, that we haven't touched.
Almost everything covered.
Okay, and in this one? Maybe the derivation of SVM, I think we kind of pushed it a little at the back. Or did we do it?
We
I
did
think
this
we ran it
SVM
in the
derivation,
system.
we did.
We did? Okay, great. Anything in here? Is there anything which is pending here? I think this is all covered. Here, I see. Okay, this is also covered. Okay, this one is also covered. Because I see the topics that I can remember. Okay, okay, these are also covered. Everything here, and even this one as well. So my job is almost done. So maybe today or tomorrow, I'll be letting the Google people know that like the next instructor could be assigned to you. Okay, so just a quick confirmation about a few things, because these things are important. Just give me a moment. I'm sharing this other device. Okay, and I'll leave you guys with some good takeaways. I'll give you some offline projects also. So in case you're interested, you can do those. These are not Goovy's official projects, but something from my side. Probably you'll cherish this. Like if you can finish it in a given time frame. So first thing I want to know is, do you guys know Bayes' theorem?
Yes.
Yes,
Okay, has this been covered?
yes,
Okay, and do you guys know that Bayes' theorem can be extended, and you can implement Gaussian naive Bayes or multinomial naive Bayes for a classification task? Any idea about this? Have I covered this or not?
Yes, you covered this Gaussian naive space.
Okay, I did, right? Okay, all right. So this is one thing that I wanted to assure. Okay, all right. I've mentioned about PCA. Okay, I've mentioned about PCA. Anything that you want to know about PCA in detail, do let me know. I'll try to cover that as well today. It's not a part of your syllabus, but I think you should know about PCA because it's an important dimensionality reduction technique, which could be asked to you like in your interviews. So this is not a part of your curriculum, dimensionality reduction, but you should know about PCA in detail. Okay, because they ask this question in general for sure. Okay, so okay, this is there. I'll also show you another dimensionality reduction technique, which is used to project your data in low dimensional spaces, just like PCA, but it is much more effective for visualization. Okay, more effective for visualization. And you can make certain decisions based on visualizing the data in low dimensional space. Okay. So we will discuss this as well. And I'll also give you some questions related to some data analysis projects. Okay, and ML projects. You guys are well versed with pandas and maybe NumPy a bit. Have you done a little bit of SciPy also?
Yes.
Okay, so I'll give you some projects. Okay, maybe 2 projects from this side. Okay, and maybe 1 or 2 projects from this side. Okay, 1 or 2 projects from this side. Okay, so these I'm going to mention today. So let's start with what we say is TSNE. Okay, and then I'll talk about PCA in detail. Okay. Or maybe I'll talk about these projects first, and then we will do the theory part, which is the boring part. Okay. So I just want to show you this TSNE implementation first. Are you able to see the screen?
Yes, we do.
Okay. Give me just a second. Give me a second, please. Okay, I believe you can see it now. Let me just check. Yes, I can see it now on the other device also. All right, so let's implement and talk about this TSNE. And I'll also probably cover a lot of interview questions for you guys. Okay. So that way you'll be able to answer most of the ML related questions. So, okay, let's start with the dimensionality reduction. Okay, so I'm going to show you this technique, which is called as TSNE. TSNE stands for, have you learned of T distribution? Have you guys been taught T distribution? Students t-test. You guys would have learned students t-test, right, in one of the prior modules? No? Am I audible?
Means that we
Yeah.
were told how to use that T value from that table. How
Yes,
to...
okay. It's the same thing. It's the same thing here. So this particular method uses the T distribution, okay, and it uses the concept of T distributed stochastic neighbor embeddings, okay, to project the data to a lower dimensional space. I will talk about what are stochastic neighbor embeddings. I'll give you the insights to this. let's see, okay, how you use it. It's very similar to your PCA. Okay, it's very similar to your PCA. So this is present in also in your sklearn decomposition. Okay, you can just type tsne sklearn. Okay, 1 second. Let's plug into this library. Okay, so let's import this. Let me take a data set to project it to a lower dimensional space. Let's choose one of the data sets. Okay, all right, let's see one of the data sets. Okay, let's use a fairly bigger one. Okay, which one do you want me to go with? You choose any of them. Okay. Hopefully, something which doesn't have many dimensions. Okay, let me see if a data set with not more than many dimensions. Okay, because decomposition takes time. You have to factorize the matrix, take inverse, which will take time. Okay, just a second. I'm seeing, okay, if there is a small data set that we can use. I think this is what we have seen before, right? The California housing data set.
Yes.
Okay, we'll use this. Okay, this is relatively smaller, 8 features. Okay. So I just want to prove a point that, okay, obviously you cannot plot this data, but you can get an idea of, okay, what type of algorithms will do better on it. Okay, so let's import this fetch California housing data set. So let's instantiate your data set first. And store the data, the features in this. Okay, and the output will be in the target. So if you remember, it's a regression data set where we have to predict the house prices, and the house prices are given in $100,000. Okay, if you look at Y, whatever number is given, you can multiply this with 100,000. Okay. So, and the features are these. So with the help of these features, the median income, house age, average number of rooms, average bedrooms, population, occupancy, longitude and latitude. Okay. So using these features, we have to predict this. Now, one thing that you have to realize is, see, there are 8 features. Okay. So if I want to plot this data set, how many dimensions would I need? Think. You're doing a regression plot. How many dimensions would you need?
2.
No. If you're doing a regression plot, you have 8 features. So you have to plot this, right? I mean, we plot X versus Y in regression.
Yes.
So how many dimensions do we need? There are 8 input features. You'll actually need 9. Okay, for one dimension, how many dimensions do we use? 2, right? 1 input feature and 1 output feature, right? So you need 2. For 8, we will need 9. 8 input features and 1 9. And obviously, we cannot plot in 9 dimensions. So one of the questions that could be asked is, like, what type of algorithm shall we use? Do we use a simple algorithm or do we use a complicated algorithm? Okay. So one of the things that dimensionality reduction can help us with is it can give us an idea. Okay, it can give us an idea how the points are distributed in the high dimensional space. Okay, how the points are distributed in high dimensional space. Maybe I'll give you an idea from say classification perspective, because that will make more sense to you. Okay, just give me a moment. I'll use a small data set. Just a second. From classification perspective, it would become more clear. Okay, let's use this. Maybe I'll use this. Okay, just breast cancer data set. Okay. This will make it more clearer. With classification, you might get a little confused. Okay, just a second. Okay, so here the objective is to identify if a person has cancer or not. Okay, so zeros and ones, as you see, so it's a binary classification data set, and these are the features. So there are 30 features approx. Okay, if I remember correctly, there are 30 features. Okay, yeah, 30 features. So using these 30 features, we have to predict if someone has cancer or not. Okay, and you can see it's a binary classification task. So one of the questions that that could be asked to you, how would you determine if I need a linear classifier or a more complex model or a non-linear classifier? See, if the data was in, say, given with two input features, I can use the two-dimensional plot, okay? Because you can plot the classes on the two dimensions. So on those two dimensions, I can easily visualize the data and I can determine if I need a linear decision boundary or a non-linear one. But with 30 features, I mean, obviously I need 30 dimensions, but I don't have, you can say, the resources to do it, neither the capability to do it. So what we will do is we will reduce these features to just say 2 or 3. So I'm going to show you how to reduce these features to 2. So we will use this method TSNE, okay, T distributed stochastic neighbor embedding. So let's call this method, okay, this TSNE method. Okay, so I'm going to call this method, this TSNE. Let's call, say, this method as decomposition, okay. So, sorry. Let's call this TSNE. I want to reduce it to 2 dimensions. So I'm saying number of components is 2. Okay. So once you instantiate this, what you can do is same thing that you have done in what we say is your PCA. So you fit your model to your data, which is in X. It is wiser to standardize your data or normalize. Basically, it is wiser to scale your data. But since it's a, I mean, toy data set picked up from sklearn, it is already standardized for you. Okay. So I'm not doing standardization. If you want, okay, I'll do this first. Okay, just give me a moment. So I'll do the standardization also. Maybe let's go with normalization. That makes more sense here. Let's instantiate these features in a particular feature range. I'm going with feature range of say 0 to 2. Okay, and then I'm going to fit and transform my data directly. Okay, and let's call it transformed X. Okay. So this I'm scaling the data here. Okay. Reprocessor. Okay, so data has been scaled. You can see that now the entire data would be, so I have just still 30 features, as you can see, 569 samples, 30 features. If you want to see the minimum, it would be 0 across all the features. Okay, it would be 0 across all the features. Okay, and if you look at your maximum, it would be 2 across all the features. Okay, now the data has been scaled. Okay, does that make sense? Is the scaling clear?
Yes.
Now, once the data is scaled, we will try to transform our data into 2 dimensions, and then we can visualize it easily because we know how to plot in 2 dimensions. So let's use the TSNE method, this decomposition. Okay. So I'm going to use the decomposition and fit it to my data, which is in transformed X. And you can directly use fit underscore transform to transform your data. And this will give you your data in 2 dimensions. Let's call it X and say in 2 dimensions. Okay, X in 2 dimensions. Okay. 1 second. It is saying that, okay, there is a parameter which is supposed to change. Okay. Currently, this is 200. It will be changed to auto. Okay. And default initialization, there is another parameter whose default initialization from random will change to PCA in 1.2. Okay, this is just a warning displayed to you. If you want to suppress it, you can import. I mean, it's not important unless you know what the default hyperparameters are. So you can say this. Okay, warnings. Stop with the warnings. Okay. All right, and now it will not show you even this message. Okay, all right. So it is transforming your data. So if you carefully see, the shape of this data will now become 569 times 2. Does it make sense?
Yes.
Okay. Now what you can do is you can plot this data and gain an understanding on whether you need a complex classifier or whether you need a non-convex, or simpler model like a linear separator, like logistic regression and maybe support vector machines in linear kernel. Okay. So let's plot this data. Let me import matplotlib. Okay, so we are going to plot this data. Let's do the scatter. We have this data with us, and we need the first axis and the second axis. Okay, this is the second axis, and we have to give colors to our outputs. The outputs are present in Y. Okay. Now, do you see that this data seems to be like kind of linearly separable? I mean, don't think of perfect classification. No data would be perfect, right? But do you see that the visualization is kind of almost linear?
Yes.
I mean, even if you do a linear decision boundary, it will give you quite good results. Yes or no? Does that make sense?
Yes.
I mean, if you really want to overfit to this data, I would say go with decision trees. If you want to do really, really well, at least overfit to this data. So decision trees would actually be the perfect ones. But even a model like logistic regression and support vector machines will give you good results. You can actually see this, okay? You can actually train one of the models like, say, logistic regression. Okay. So I'm going to show you the results in 2 dimensions as well as high dimensions. So let's take this data. Let's first train a model. Do you want me to split this data also? Or shall I directly show you the train accuracy? What would you recommend? Do you want me to split this data into train and test? Because I'll have to run it again otherwise, in that case.
No.
Okay, I'll just train a model and we'll show you the train accuracy. So you can gauge an understanding on if the model is doing good or not on the examples. So let's take logistic first. So logistic regression. And this should give you an idea that, okay, logistic regression does fairly well on the actual data set. Okay, on the actual data set. Okay. I'm giving a random state here so that, okay, you get the same results as well. I'm fitting it on transformed X. Okay. One second. The model has been fit. I'm computing the accuracy, let's say. So this was on the original data. Okay, I'm computing the train accuracy. Okay, please keep that in mind. Okay, do you see the accuracy seems to be very, very high?
Yes.
Okay, I mean, it's obviously because when we look at in low dimensions, right, this method gives us a good idea that, okay, 98% of the samples are almost correctly identified. Okay, now let's see if you use these reduced dimensions. See, please understand this, if you're using these reduced dimensions, obviously the performance might suffer a bit because you're losing on information, right? From 30, you came to, just 2 dimensions. So your results will be slightly off or might be slightly better as well in some cases. Okay, your results may be slightly off, maybe say 96% or 97%. Or it might be slightly better in some cases. Okay, if I use a decision tree, it will become better. Okay, if I use a decision tree, this will even become better. So I'm going to use this X2 dimensions. This was the transform data by TSNE. Okay. And let's compute the accuracy score on this. Okay. It will not touch 100 for sure, because as you can see in 2 dimensions, it is not able to completely separate it. We see that it is just slightly off. Do you see that it is just slightly off, as I mentioned? See, the reason is with just 2 dimensions, you are able to achieve the same performance as you had in 30. Almost the same performance as you had in 30. So don't you think that if you need, let's say, a smaller data set, if you have a device with probably limited compute memory, wouldn't you prefer a reduced data set? Yes or no? Okay. So these kind of things, they give you an idea of, okay, what kind of model will work better. If you use a fully grown decision tree, this can even outperform this as well. Okay, this can even outperform this as well if you fully grow it. Okay, if you fully grow it.
How does it take which two dimensions to keep? Like in
No, it's not taking the it's projecting the data onto a low dimensional space.
So it's projecting the data onto two-dimension space, right? In TS, we set the number of components to be 2.
Correct.
So in that case, which
So it
two?
is not taking the 2 features out of 30. You're interpreting it incorrectly. It's like a PCA technique which projects the data.
Okay.
It's a PCA technique which projects. See, there are 2 types of dimensionality reduction techniques. One is called as feature extraction. One is called as feature selection. You're talking about selection where you explicitly pick a subset of features.
Right.
Okay. This is not that. This is essentially, you can say you are multiplying a matrix which is non-linear with your original data. So what is my original size? 569 times 30, right?
Yes.
Okay. Do you think that if I multiply this with a 30,2 data set, I will get 569,2?
Yes.
Okay. Does it make sense?
Yes.
That is what PCA tries to find out. But am I picking the top 2 features from it? No, right?
No.
So it is similar to PCA, but it is a non-linear dimensionality reduction technique. Okay, it is similar to PCA, but it is a non-linear dimensionality reduction technique. I will talk about what it does in detail in just a bit. Okay.
Okay.
So it's a feature extraction technique, not a feature selection technique. Okay. It extracts new features from your data. It is not basically just selecting any 2 features and keeping those. No, it's not doing that. It's not similar to recursive feature elimination. Is this clear?
Yes. So in SVM also, like we do like this only, right?
In SVM, you project the data, but to a higher dimension. Here you are reducing the dimensions.
Okay.
SVM increases the dimensions with the help of kernels.
Okay.
Here we reduce it. Okay, it's the other way around essentially. Okay, so this is the TSNE. I mean, if you want to go for a little bit more complex model, obviously it will improve. But let me tell you, simpler models often do better on real world data sets. If you choose a more complex model, it is likely to overfit. Okay, so just to show you, I mean, if you use, say, a decision tree model, okay, your results might slightly improve as well. Okay. So let me use a decision tree classifier. Okay. Okay. Your results might slightly improve as well. Okay. All right. Do you see it becomes 1? Because now that you have fully grown it, think about, okay, what will happen? Okay, let's say if I use, so I've done it on a transform data set right now. Don't you see that like this type of data, if I just draw a line here, this purple data would be correctly identified to the right of it.
Yes.
And then it will make smaller partitions for these purple points. Yes or no?
Yes.
So decision tree it's a more complex model, right? It will give you partitions for your what we say is overlapping points. But in general, these results will lead to overfitting because you're doing very well on the trained data. It is not necessary that a point which is given to you here, where my cursor is, will actually be a purple point. It will mostly be yellow. So in real world, your performance would deteriorate. Okay, if you assume it to be purple. Okay, so that is why it is not advisable to create a partition in this case, even in this case. So the more points are likely to be yellow in this region, not purple. But a decision tree, when you are doing it right with the help of train set, it is creating partitions for each of these points, each of these purple points. Okay, so this point is essentially an outlier if you think about it. Okay, so you can actually discard it from your data. All right. So let me tell you what TSNE does, okay, at least to some extent, so you have an idea for this. Okay. What TSNE does is this. So TSNE tries to preserve the geometric, you can say, topology. Okay. Topology in the low dimensional space. Let me give you an idea what I mean by this. And one more thing before I stress on this geometric topology. See, please note that TSNE is a non-convex function. Okay, so it can give you different solutions. Okay, it's a non-convex function, so it can give you different solutions. All right, so your results can be different if you run it with a different random state. Do you want me to show? Okay, I'm just showing you that. Okay, the results of TSNE will change. Yeah, if you just put in a different random state. Okay, it is not necessary it will always converge to the same data set. See, I'm running it again. Okay, just see this. Okay, the results might change. Do you see the results change actually?
Yeah.
Okay, so just wanted to highlight that it's a non-convex function, but still you can see that. Okay, the data is linearly separable or not. It is, right? It still gives you an idea that you can use a linear classifier to separate the data. So please note that it's a non-convex function. So it can end up in local minimas, but it still gives you an understanding of which, so it probably gives an understanding of the complexity of the model that we should choose. Okay. Okay. So this is an excellent tool. Another is like what is meant by preserving the geometrical topology. So I want you to think of maybe in terms of this. So if you look at say, I'll just give you an understanding of like this. Maybe say there are 3 points, xi, xj, and xk. Okay. So think of these triplets. Okay. So think of all possible triplets of points. Okay. You can think of all possible triplets of points. So my question is this: if xi and xj are closer, okay, in 30 dimensions, you are projecting this data xi and xj now in 2 dimensions. Can I say that xi and xj should be closer? Yes or no? When you are trying to project the data from 30 dimensions to 2 dimensions, let's say if this is xi and xj, okay, these 2 points are xi and xj. So in the 30 dimension space, what do you expect? These points will be far away or close by? Wouldn't you like to preserve?
For the dimensions, it will be far away, and if we reduce the dimensions, they become more closer.
They become more closer, but the idea is this. See, that is why I chose a triplet, not a pair. Obviously, when you project the data from 30 dimensions to 2 dimensions, the distance decreases, right? Yes or no? Any example that you take from so the distance would decrease because previously you were taking the difference between 30 dimensions along 30 dimensions. Now you're just taking the difference in 2 dimensions. So the distance would proportionately decrease. But the idea is now look at this third point, which is xk. Okay. So if xk was far away from xj and xi, the idea is even in 2-dimensional space, xk should be proportionately away from xi and xj. Xk should be proportionately away from xi and xj. Okay, that is the whole objective of this algorithm TSNE. What is meant by the topology is the relative orientation of points in the original 30 dimensions. Their relative distance should be preserved in this lower dimensional space, in this 2-dimensional space. So that is the objective that TSNE tries to achieve. Okay, that is the objective that TSNE tries to achieve. Now, how it achieves this, I'll give you more intuition on this. Okay, so maybe I'll draw a figure and probably that can give you an idea in more sense. Okay. Okay, just give me a second. I'll just share my screen again here. So the concept of geometric topology or simple topology, preserving the orientation of points and their relative distances, is quite popular in literature. And it tends to work very well. Okay, let's see this. Okay, and see, I can only draw in 2 or 3 dimensions, so I can just give you an idea. So I'm giving you the idea in 2 dimensions. Okay, assume that the number of dimensions are 30. Okay, assume that number of dimensions are 30. Okay. but I'm going to show you in 2 dimensions, okay, how to understand this. See, if I want to figure out, okay, if I want to figure out, let's say this is, okay, this is how the data looks like. Okay, this is how the data looks like. If I ask you, if this data was in, say, 30 dimensions, obviously it is in 2 right now, but if you think about it, if I ask you, what is the distance between, say, this point and this point? Okay, let's say this is xi and say this is xj. What do you think the distance is? Is this the distance?
The maximum distance.
No, is this the distance that you will be defining?
Yes.
No, it is not. So that is the issue right now. Okay, that is the issue right now. See, the idea is this. When we actually try to preserve the relative orientation, okay, when we try to preserve the relative orientation of points, okay, what would happen is if you use this distance, okay, if you use this distance, the idea is you are trying to preserve the displacement. It is not the distance. Am I correct to say that?
Yes.
This is the displacement, right? Euclidean distance between points. This is actually the shortest distance if you think about it. Okay. Now think of this. If you really want to see what is the distance between these points, so what you should do is you should rather think of these points as like the connecting edges. And this is what the total distance should be. So this is what the total distance should be. Okay. Now, why am I saying this? Okay. So you can think of it like you have a road and you want to reach from one point to the other. So can you directly go from here to here? So the road is built like this. Okay, the road is built like this. Maybe there is a river or like you can say a swamp here. So can you go from xi to xj directly?
No.
No, right? So the idea is this. Whenever you are trying to preserve the relative orientation of points, okay, you try to preserve a distance which is called as the earth movers distance. Okay. This is called as earth movers distance. This is also called as geodesic distance. They are synonyms. Okay. This is also called as the rubber band distance. Do you get an idea of what this distance is? Okay. People also call it as the thread distance, or and there are many names for it. Okay, let's see what this earth movers or what this geodesic is. Okay.
Can I say like I'll try to move on a path that covers all the data points of my data set?
No,
Or maximum data points of my data set?
No, not like this. I shouldn't say you should cover all the points. Okay, let's say this is how the data is. Okay. So what you can think of is like this. Okay, you will try to reach from point xi to xj. Okay, with the help of you can say a thread or a rubber band. So if I fit a rubber band to it, how would the rubber band go? Like think of the tightest rubber band that you can do to travel from xi to xj. This would be this, right?
Yes.
The tightest rubber band I'm saying. Okay, the tightest rubber band that you want to fit. That is like the earth mover's distance. So it's like saying I want to travel from one location to the other. So you can think of these points as the nearest cities to which you can travel. The roads are there through which you can travel, and then you can get to your destination with the help of these connecting roads. Okay, this is called as earth mover's distance. So to essentially define the distance between xi and xj, the concept is of nearest neighbors. Okay, the concept is, let's say if this is point xi and this is point xj, I want to know the distance between xi and xj. This is defined as the sum of the, this is the important concept to preserve the orientation. Okay, I'll talk about what is this the sum of. So the idea is this: you try to move in the direction of xj, okay, and then try to see what are the nearest neighbors. So in how many points do you see the nearest neighbors of xi? So let's say I'm looking at three nearest neighbors. This is one, and maybe this is one. Does it make sense?
Yes,
Which is the closest neighbor?
the first one.
The first one.
This is D1. Okay. All right. Now look at, you are now at this point. Which is the nearest neighbors? Which is the three nearest neighbors of this point? Maybe this one, and maybe this one. Yes or no? So you will reach to this point, which is D2, the closest neighbor. Again, if you keep on repeating and you move in the direction of say Xj, okay? So you have to pick that point, which is the nearest neighbor, and the displacement of this point has to be nearest. Okay, displacement of this point has to be nearest. So obviously I'll pick that point, right? Yes or no? Oh, sorry, I will be picking this point, my bad. I will be picking this point, sorry. I made a slight, I'll be picking this point. Yes or no? If I want to fit the tightest rubber band. Does this make sense? See, this point has
So-
less displacement with respect to Xj, right? Yes or no? So pick one of the nearest neighbors that has the lowest displacement. You have to go towards Xj, right? Not away from Xj. Is this clear or not?
So to move towards Xj, I'm repeating the process continuously with the nearest neighbors, and then I'm reaching the Xj.
So
This is what-
you have to pick that nearest neighbor which has the lowest displacement with respect to Xj at every step.
Okay, so from that point, then I'll do the same step until I reach the Xj.
Until,
This is
yes,
what-
until, so you will essentially see that you will get the tightest set of points, okay, that are, you can say,
connect to
you,
the X.
that are surrounding these connecting roads, okay, connecting points.
Okay.
So this is the sum of these distances, okay. Now, why are we using these distances and not the direct distance? Can I say that locally the distance is, okay, how do you measure the distance between this point and this point? See, can I say locally the distance is Euclidean?
Yes.
However, if you would have chosen this direct Euclidean distance, would it have been appropriate? If you want to preserve the topology of the structure, okay, this is how in 2 dimensions the data should look like. If you directly pick this displacement, do you think it would have been all right? No, right? Yes or no?
No.
The relative distance of this point would have been lost with respect to other points, right?
Yes.
Okay, if you directly pick the displacement as the purpose. So the idea is you use this notion of local distance being Euclidean. Okay. So locally the distance is Euclidean. However, globally, you are measuring these Euclidean distances to reach to your destination. Okay. You are measuring these Euclidean distances to reach to the destination. Okay. So this distances is what this TSNE is trying to preserve in the 2-dimensional space. Is this clear? So the relative proportion of this total sum D1 plus D2 plus D3 and so on, this will be preserved for every possible pair or every possible triplet in the high dimensional space. Sorry, in the low dimensional space by projecting the data which was there in high dimensional space of number of dimensions being equal to 30. So when you project this from 30 to 2, the relative proportion would be preserved. Okay. A relative proportion would be preserved. So if you can preserve the relative proportion, that also gives you an idea, okay, what kind of classifier to choose or what kind of regressor to choose. Okay, the orientation of points helps you decide. Okay, so this is a very effective approach used as like the pre-processing criteria for many classification tasks. Even for regression tasks, you can use it. You just see the orientation of the points, and on the basis of that, you that you can actually look at what we say is a pairwise plot. Are you guys aware of Seaborn library?
Yes.
Have you used this pair plot?
Yes, just like we have seen what pair plot is, and
Okay, so pair plot is nothing but, okay, let's say if you have, say, 30 features, okay, so it would be a 30 cross 30 grid. Okay, if you have 30 features, it will be a 30 cross 30 grid. So along the diagonals, okay, along the diagonals, you will see, you can say the distribution plot. So this would be what? Can I say this would be feature 1 times feature 1? Yes or no?
Yeah.
So here you are trying to have like a distribution of features. Okay. Assuming the feature is real, can I say that this would be some kind of distribution, maybe like this or maybe like this? So x1 is on the x-axis, and then you are simply plotting the histogram. Does that make sense? So essentially on the diagonals, you will see the histogram of the features. How many diagonal values will be there?
30.
30. So this would be histogram of x2, this would be histogram of x1, this would be histogram of x3. Is this clear? Along the diagonals, what is given to you? Yes or no? Along the diagonals, do you understand what would be the values? That would be the histogram of all the features. So it would be histogram of feature 30 at the end. Okay. Now let's see at this cell, what would you get? Okay. Let's say there is this some cell I comma j. Okay. So this is basically for feature I and feature xj. Can I say this data that you are seeing would be symmetric? Maybe say this is somewhere xj and xi. Can I say that this data would be symmetric?
Yes.
Okay. So here what you see is what we say is the scatter plot. So here what you see is the scatter plot. Now my question is this: if in some cases in the scatter plots, okay, you are trying to put the two features along with that, let's say you're doing classification, let's assume this, and you are plotting the output y. And if the data becomes linearly separable, can I say that I can directly pick those two features and do my classification? Assuming the data is linearly separable. Yes or no? See, I give you two features, okay, and I tell you the outputs. Can you not plot it using a scatter plot? You can, right?
Yes.
And if the data comes out to be, say, almost linearly separable or linearly separable, okay, almost or linearly separable, can I say that, okay, the data being linearly separable and I need only two features for it to separate my data? Yes or no?
Yes.
I hope that makes sense. Okay. So scatter plot also gives us an idea of okay, what features are important, what features are correlated. Okay, how would the scatter plot look like to understand that if two features are correlated or not? Any guesses? How would the scatter plot look like to say that the features are correlated? Okay, do you see that? Okay, are these features correlated?
Yes.
Yes, right. Highly correlated, by the way. If xi increases, xj increases. What about this type of features? Still yes, right? If xi increases, xj decreases. Okay. But what about this kind of scenario? Think. When xi is constant, do you see different values of xj?
Yes.
So is there any relationship? No,
No.
right? So they are independent. Okay, maybe think of this direction.
No
What can you
matter
say?
what, no matter what is the value of xi, xj remains same.
Xj remains same, right? So they are independent. Okay, so what type of features do you want?
The
The independent kinds. Okay. So pair plot can actually give you a lot of insights. Okay, pair plot can give you a lot of insights. So make use of pair plots, make use of this TSNE to draw conclusions about like what type of models you should use. Okay.
so pair plot is helpful only when I have to do the feature two feature extraction, right?
I mean, this kind of gives you an idea, okay, which features are highly correlated, and with the basis on the basis of that, you can drop some of the features, right? This is like essentially you can do the correlation between the features and make this decision. Also, let's say if for a particular pair, the data becomes perfectly linearly separable, do you think you need any other features at all?
No.
No. So just pick those two. You can discard the other features at all directly. Okay. Because see, in most of the cases, your objective is to get a reasonable performance. Why? Because sometimes you just have to give the result, right? you don't have to wait to get the most optimal performance. I hope you get this idea, because the data might be humongous. You will not be, see, currently you are thinking as if the data is just 100 points, 200 points. Let me tell you, when you go and work in the industry, you will frankly have 10 million points or more in most of the data sets that you work with. So even if you are able to remove a few features just by drawing this pairwise plot, this will also take you a lot of time to draw. Okay, this will also take you a lot of time to draw, by the way. So this is like a pre-processing step, which kind of helps us give the right directions. Okay, what to do, what not. Is this clear? Yes, people, is this clear? Is the intention of the pairwise plot clear or not?
Yes.
Okay. Let's see, okay, an understanding of PCA. Okay. So this is to tell you from what we say is from a generic standpoint. Okay. See, PCA is a linear dimensionality reduction technique. You can use PCA also, just like you use TSNE. Okay. But PCA does not preserve the topology. Okay. So don't use PCA just to get an understanding of what type of complexity you should do. Okay. But if you want to do, if you want to save your features, essentially, if you want to reduce the number of features, then you use it. Okay. Don't use PCA to gauge like what complexity of classifier you should choose. However, if you want to just reduce the features, then you can do this, compare the performance. And if PCA leads to almost similar performance, then make use of PCA. So what I'm saying is, let's say if you directly use the data set, you get say 80% performance. And upon doing PCA, you get say 79.2% performance with just 3 to 5 features. Then PCA is something that you can think of, because the performance hasn't changed much. But don't gauge by doing PCA after projecting the data onto 2 and 3 dimensions. So PCA will tell you, okay, now the data is linearly separated. So PCA does not preserve the topology. So the original topology might be entirely different. Okay, so don't think in terms of that. So let me tell you what PCA tries to do and how it is different from TSNE. Okay, at least you should know the intuition behind it. So see, PCA is an unsupervised technique, just like TSNE. Okay, it only uses the features. See, if you remember, when I applied TSNE, did I use Y anywhere? When I called the fit underscore transform function, did I use Y anywhere? Even when I called the fit function, did I use Y? I did not. So even this is unsupervised. Okay. Even this is unsupervised. All right. So the idea here is this. Again, I think I have already discussed this to some extent. Given some data of n cross d, I want to project it to some n comma k, where k is less than d. So what I do is I have to find this matrix of size d times k. Yes or no? Does this make sense? So if I multiply this matrix X with this matrix D comma K, then I will get N comma K. So finding this D comma K is the objective of this PCA. Now, how does it do it? I'm going to give you an intuition. Okay. And what does it try to preserve? Okay. So TSNE tries to preserve the relative orientation of the points. PCA tries to preserve the following things. Okay, let's see this. I'm giving you an example from 2D perspective. Okay, let's say this is how the data is. Okay, so imagine we are trying to do classification. So we have these two features. Maybe say this is how the points look like. Okay, imagine this is how the data looks like. Okay, my question is this, or maybe say this is how the data looks like. Okay. Okay, if this is how the data looks like. Okay, can you forget maybe say the labels for now? Don't think of the labels right now. So think of this as points which I'm giving you. So in the data, I'm just giving you x1 and x2. In the data, I'm giving x1 and x2. Okay. Don't think of the points, the labels right now. Okay. Don't think of the points right now. Please keep this in mind. Okay? Don't think of the points right now. The outputs. I'm saying that outputs are not given to you. This is just for illustration. Okay. Now my question is this. This data, do you agree it is two-dimensional? Yes or no?
Yes.
Okay. Now the question is, if let's say you were doing classification, okay, if you were doing classification, do you really need both the dimensions? Assume that there was output which was given to you. So do you really need both the dimensions?
Can you repeat the question?
I'll repeat this question again. Okay. Do you really need both the dimensions to do 100% correct classification? Okay, let's say if I give you the values of x1 only.
Looking at this data, no, with x1, x2 remains almost the same. So we can skip.
No, just think of for now, if I just give you the data of x1, okay, do you think only by looking at the data of x1, you can, do perfect classification? Yes or no? How do you do classification in one dimension? In two dimensions, what is it that you identify? A line. In one dimension, what is it that you identify? A point. So if this is the separating point, can I say that in x1 I can do it perfectly?
Yes.
Yes or no? Even in x2 I can do it perfectly? Yes or no? So x2 would be this point. So anything above this is going to be an x, and anything below this is going to be a triangle. Yes or no? Does this make sense? Is this clear or not? See, essentially, do I need to keep both the features? That's the question. No, right?
No.
I can use any of the features. But for this given example, let's say if I use a combination of x1 and x2, okay? So let's say this is a line. Typically, what is the equation of a line?
Y
Equals to mx plus c, right? Okay. That is how we say it. So what is y here? X2, right?
Yes.
Okay. So can I say the equation of this line would be something like x2 is equal to m1 x1 plus c?
Yes.
That is how you write it, right? So can I say, so I'll just multiply this with a constant, okay? So can I say this is nothing but m2 x2 plus m1 x1 plus c is equal to 0? Yes or no?
Yes.
M1 M2 can be negatives also, that's also fine. It's just a constant, right? So this is the equation of this line, okay? If you look at this line, what is it? Okay, can I say this is having, this is the value c, okay, if you currently see. So when I put x1 and x2 as 0, what do you get? You get c, right? Yes or no?
Hmm.
So this is what the y-intercept would be, where this line hits the y-axis. Is that clear?
Yes.
Okay. And now I want you to see carefully. Can I say that I am taking m1 component of x1 and I'm taking m2 component of x2? Okay, this is the m2 component of x2. Okay, I made it slightly like this. Okay, m2 component of x2, and this is what m1 x1 plus m2 x2 is. Yes or no?
Yeah.
So see, the slope is, how do you define the slope for a line? How do you define m? See, we say y is equal to
Y divided by
mx plus c is the slope, right?
Yes.
So currently, what is y? X2, right? Yes or no? Currently, what is y? My x2. Okay. And if I want to make the slope of, can I divide this x2 by this x1? I am having this as m1 x2, right? m2 x2. This equation, I'm writing it as m2 x2 equal to minus m1 x1 minus c. Yes or no? This is what my equation is. Yes or no? Okay, look at this. What is my equation? If you can directly relate to it. What is my equation? This, right? m2 x2 plus m1 x1 plus c is equal to 0. Yes or no? Okay. Let's write this in terms of x2 only. Okay. This would be the equation with a minus sign on both sides. Okay. Is this clear? Okay. And what would be x2 now? Can I write this as minus m1 by m2? Okay. Into x1. Okay. Minus c. Yes or no? So essentially, what is the slope right now? Minus m1 by m2. Do you see that? Yes or no?
Yes.
And how do you define the slope? The theta, tan theta. And what is tan theta? Perpendicular by base. What is perpendicular? M2? Yes or no? Do you remember a little bit of trigonometry? And what is base? M1. Is that clear or not? Yes, people. Is that clear or not? So here you are defining it x1 in terms of x2. You can define, here you are defining x2 in terms of x1. Can I not define x1 in terms of x2? I can, right? Okay.
Yes.
So do you think that this perpendicular by base, the proportion of this, will it be any different if I measure it here? Will the theta change if I measure it here? Will the theta change if I measure it here now? If this is perpendicular, if this is base. Do you think the theta changes here? No, right? It is what we say is the corresponding angles.
Yes.
So wherever you take this line, along this line, the theta remains the same. Anywhere wherever you pick. Okay, anywhere wherever you pick, the theta remains the same. Okay. Now I want you to think about this carefully. So currently I'm using one dimension, right? Which is a combination of x1 and x2. Yes or no?
Yes.
Yes.
Okay. Now if you look at the projection of these points along this line, okay, which is this. Here, 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 here. I mean, my projection is bad. Okay, it should be 90 degrees. Okay, so it would be here like this, 90 degrees. This is called as the projection of the points. Does it make sense now? Projection is called as the 90-degree projection of the points. Okay. So do you realize that this would be the projection? Yes or no? Is this clear or not?
Yes.
Okay. Now my question is this. Do you think this line is also sufficient to separate between accent triangles? If you put this as your threshold, anything above this is an X, anything below this is a triangle. Yes or no?
Yes.
Okay. Now, which line do you think is better? X1 is better or X2 is better, or this line which I made is better? Where do you think you got the maximum separation? Just look at this carefully. Where do you think you got the maximum separation between triangles and X's?
The line which you drawn.
Along the lines which I made, right? Okay. Yes or no? Along the lines which I made. This line.
Yes.
So can I say that if, okay, and what should be the objective? Okay, if you think in terms of finding this line where the separation is maximum, what should be the objective? Can I say my objective would be to ensure that the spread of the points along this line should have to be the maximum? Yes or no? If I want to get maximum separation between the points, can I not say that the spread of the points along this new line has to be the maximum?
Yes.
Yes.
And that is what PCA does. So what PCA tries to ensure, okay, what PCA tries to ensure is this. So PCA tries to it tries to estimate new dimensions, okay, where the variance is maximum. Okay. Variance is through which you measure the spread, right? Yes or no?
Yes.
Okay. So if you think about this, okay, I'll maybe give you more examples here. See, currently I'm showing you with the perspective of classification. Now ignore all the you can say class labels. So I can still find a line made out of x1 and x2, which is m1 x1 plus m2 x2 plus c equal to 0. Okay, where the variance is maximized without worrying about the labels. Okay, forget about classification for now. Do you think it is possible that if I try to maximize the variance between the points, I can get a better classification just by one dimension without worrying about the points. Is it possible that I get a better separation? I can, right? I may not. Yes or no? When you try to ensure that the points are well spread out, do you think it will do you any harm? Think of that. When you are projecting your points onto a new dimension where the points are well spread out, do you think it will do any harm? Even if you're doing, say, classification or regression or any other task?
No.
Don't you think it is a good thing to do?
Yes.
Because the points are becoming much more clearer. I mean, they are becoming much more distinguishable. Okay. Another thing that I want you to figure out is this, or maybe see is this. Okay. Now forget the labels. Okay. Forget the labels. So what do you want your dimensions to be? Originally, if you look at x1 and x2, what can you say about x1 and x2? In general, the way I am drawing these x1 and x2, why do I draw it like this? Any guesses? Why do I draw it at a 90-degree angle? Any guesses?
Because when I'll pass a line from these points, these should be parallel.
No. Why is it that I draw x1 and x2 as parallel to each other? Like when I'm drawing any dimensions, right? I always draw it parallel. See, even when I'm drawing the third axis, say x3, the z axis, I draw it as perpendicular to x1 and x2, right? Yes or no? That is how I say it.
Yes.
Why?
So that I can.
Any ideas? No, they are independent. What is a dot product of two features which are independent? How do you define the dot product? A into B into cos theta, right? And what is cos pi? So I hope you get this idea. Why is it that we always draw perpendicular axis and not at 80 degrees or 70 degrees or 60 degrees? Because I want these axes to be independent of each other. These are essentially features, right? Yes or no?
Yes.
X1 and X2 are features. When I make this assumption that, okay, but are they truly independent when you draw the scatter plot? They are not, right?
No.
Okay. So here, let's say I have drawn this one axis, which is m1 x1 plus m2 x2 plus c equal to 0. I can make one more axis, right, which is perpendicular to it. I can make one more axis which is perpendicular to it. Yes or no? Does that make sense or not?
Yes.
So when I am giving you two features, how many features can you make out of it? You can make two features out of it, right? One is where the spread is maximized and you draw orthogonal to it. Does it make sense? So it's like, see, it's like saying that you had this type of data and now you are just rotating it like this. Is this clear? Yes or no? So you have just rotated it like this. Okay. I mean, I hope you are able to see my face. We've just rotated it like this. So this is still 90. This is still 90. Why we are doing this? Why? Because we want along this line the variance to be maximized. Is this clear? So we want to find a new dimension where variance is maximized. Now think of this. If all the variance is maximized along this dimension, do you think you need the second dimension, this dimension? If you look at, so let's say if the data was like this. If the data was like this. Okay, exactly horizontal. Okay, exactly horizontal. Along which axis the variance is maximized? Along which axis the variance is maximized? Let's say this is x1 and this is x2. This is how the data is given to you. All these points are exactly parallel to x1. Think about this, along which direction the variance is maximized. It is x1 only, right? Yes or no? Do you think there is a need for x2?
No.
No, right? Because x1 and x2, they are now totally independent. Okay, I don't need x1 at all. So the objective is, okay, the objective is, if I give you the data which is, let's say, slightly spread out, okay, if you find a new dimension along which, let's say, you have maximized 99% of the variance, and here it is just 1% variance which is left out. So basically, if you project along these lines, the data are very, very close. Do you think this dimension would be useful at all? Do you think this dimension would be useful at all? So if you draw the perpendicular of this would look like this. Along which dimension do you think the variance is maximized? Along x1 or x2? Where do you see? Where is the spread more? Observe the spread. Along x1, right? Yes or no? The new axis that I made. Okay, along this x1, the spread is more, right? Can you see that the spread is more? I mean, in terms of this, like with respect to x1 also? With respect to the original x1.
Yes.
Okay, so the point that I'm trying to make is you are trying to find new dimensions along which the variance gets to be the highest. So if you are able to capture most of the variance with just one dimension, you don't need a second dimension. You put a constraint that, okay, I want only 99% of the variance in this. Okay, so I just need one dimension. I will not even need the second dimension. If your constraint is 95%, and let's say this captures 90% of the variance, then you need both the dimensions. So think of this. If your data is projected in, it's present in 30 dimensions. And now I'm trying to find the very first dimension along which the variance is maximized. Let's say that particular dimension captures 60% of it. Think of this carefully. Given a data with 30 dimensions, okay, given a data with 30 dimensions, don't you think I can rotate the dimensions such that I will get 30 new dimensions?
Yes.
I mean, I can rotate it, right? Yes or no? You just saw it. In 2 dimensions, I rotated and it got like this. So I'm saying that rotate the new dimension such that the variance along the first dimension is maximized. Okay, such that the variance along first dimension is maximized. Okay. All right. So you can figure out what is the variance along the first dimension. Let's say this is the variance along the first dimension. You draw a perpendicular to it. Can I say this would be the second dimension? Yes or no?
Yes.
That is why we say x1 is perpendicular to x2, right? So I can figure out the projection of this. So this is capturing 60% of the spread. Maybe this captures 20% of it. And now I draw perpendicular on for both x1 and x2. So this would probably look like this. So this is the third dimension. Maybe this captures, say, 15%. And if my constraint was, say, a total of, say, 80%, or maybe say 85%. So if I only use the 3 dimensions out of 30, do you think my threshold is satisfied? If I use just 3 dimensions, do you think these 3 dimensions would be enough to do the task? Yes or no?
So constraint is 85, then
So 60 plus 20 plus 15. What is this number currently?
yeah,
85, right? I mean, sorry, this is 85, but your constraint was 85. Okay, this was your threshold. So if you would have used 2 dimensions, what would be the variance capture? 80%, which is not satisfying 85% threshold. Now I go to one more dimension. Here I got 15%. So here you jumped the threshold. So you are okay with 3 dimensions. Now you don't have to go beyond 3 dimensions. That is what I'm saying. So you put a threshold and decide, okay, how many dimensions do you actually want? You want 3, you want 4, you want 5. It depends on what threshold that you set. Let me tell you, for any type of data set, right, you would get very high significant boosts if you want to preserve the variance. So from 30 dimension, it would just boil down to maybe 3 or 4. From say 10,000 dimensions, it will boil down just to maybe 700 or 800 if you do PCA. Is this clear?
yes.
Okay.
So,
So, but the objective is, yes, go on.
so PCA will basically do the reduction of the features, and then between that it will give us the best dimension with a threshold that we were setting.
So the idea is PCA will try to find out new dimensions where variance is maximized and they are perpendicular to each other. So here, like, let's say if I give you the original data in 2 dimensions, is it guaranteed that the variance is maximized? No, right? I mean, you might be given some points like this. Is it guaranteed that the variance is maximized? Probably not, right? But if you rotate the data like this, okay, maybe something like this. Do you see that the projection becomes actually even much more significant?
Yes. Yes.
Okay. I mean, the idea is if you rotate the data and let's say along this dimension x1, the variance has now become more. This new dimension, okay, let's say new d1, and this is new d2. Okay, this is just a rotation of the axis, right? Here, so new d1 is some m1 times x1 plus m2 times x2. This d2 is nothing but perpendicular of this, right? Again, some component of x1 and some component of x2. Yes or no? I mean, I should have drawn it like centered around the origin. Okay. I should have drawn it like this, centered around the origin. Okay, centered around the origin. So that's how you can call it as a rotation. Yes or no? So the idea is find this new dimension. If along this new dimension, your criteria is met, you stop at this one dimension. If you need the second dimension also, use both of them. But now use this new projected space instead of this. Okay. If this is not clear, let me show you mathematically what I mean by this. Okay. All right. See this. Okay. See this carefully. Okay. Perhaps this would give you an understanding now. My data is given in 2 dimensions. This is x1, x2. Okay. I want to project it back to say 2 dimensions. Just think about this clearly. This is n comma 2. I want to again project it to n comma 2, but this is new space. Okay. This is new space. Okay. Let's say this is Z1 and Z2. This is new dimensions. So what should I multiply it by? What should I multiply X by? Yes, people. What should I multiply X by? A 2, 2 matrix, right? Yes or no? See, if you want to get this matrix Z, the transform data, what should you multiply X by? A 2, 2 matrix, right? Yes or no? N comma 2 multiplied with 2 comma 2. What do you get? N comma 2 back, right? Okay. Now let's look at the first sample here. Let's say this is A1, A2. Okay. This is the first dimension. Let's call this as M1 and M2. Okay. This is the first dimension. Okay. So what would be this first value? Think about this. This would be M1, A1 plus M2, A2. Yes or no?
Yes.
Is this clear or not? So what did you actually do? You just used the M1 component along the dimension x1. This is what this is. Okay, if this is x1, this is x2. What you are saying is when you are projecting it like this, you are using M1 weightage of x1. Okay, you are using this M1 weightage of x1. Okay, and you're using this M2 weightage of x2. Does this make sense? Don't look at the second dimension now. Maybe like this. Is this clear or not? Can I say that along this line, this is how it looks like. Okay, look at this theta. Can I say that along this line, you are using this M1 as the weightage, and along this line, you are using M2 as the weightage? Yes or no?
Yes.
Okay. So this is the first dimension. Look at for another point. Let's say this is B1, B2. What are you doing? You are taking M1 component of B1, the value of x1, plus M2 component of B2. M2 is coming from the x2 component, this x2 component. So can I say that Z1 entails M1 component of x1 and M2 component of x2? Yes or no? Is this clear or not? Yes, people. Is this clear? Think. If it's not, ask me again. See, along this new line Z1, how a point would be, so let's say if this point is say A1, A2. Okay, if this point is A1, A2, I want to project it along Z1. What should I do? I want to project it along Z1. What should I do? I'm telling you that this line Z1 has M1 component of Z1 and M2 component of Z2. Don't you think this would be M1, A1 plus M2, Z2? Whatever this is, let's say whatever this is say 90 degree. So this is where it would be projected. This is the Z1 component. Now, where would be the Z2 component? Z2 component would be just orthogonal to it. This is Z2 component. Okay. And what is the Z2 component? You will say that, okay, let's say this is N1 and this is N2. Let me say this is say E1 and this is E2. Okay. So this time you are saying wherever you are projecting this data here, okay, wherever you are projecting this data here, let's say this is 90 degree here. Okay. You are essentially saying that this line is essentially Z2. Okay. I mean, I should draw this. Okay. My drawing is essentially bad. Okay. Let me make it here. So let's say this was a line Z1. Now you are making the line Z2 like this, which is orthogonal to it. This was the point A1, A2. Okay. So here the projection of this point was, this was M1, A1 plus M2, A2. Here the projection of this point would be 90 degree component. This would be E1, A1 plus E2, A2. Is this clear now?
Yes.
Okay. So essentially now you are projecting each point such that the projection along this line Z1 has to be maximized. That is the objective function. Find the Z1 such that the projection of each of these points has to be maximized. Okay. Even along these lines, the projection has to be maximized. Okay. So even if you maximize along one line, you just take an orthogonal of the second one, that will be taken care of. Okay. If you do it just along the first dimension, you don't have to do it along the second. It will be automatically taken care of. Okay. That is the objective of PCA. The goal is to ensure that these points are well spread out. And if these points are well spread out, it is likely to be helpful in classification. It is likely to be helpful in even regression. That is the objective. You essentially don't need the entire dimensions. You need or maybe just a few dimensions out of the original ones. If you try to maximize the spread. Okay. If you try to maximize the spread. That is the whole objective of your PCA. Okay. So I hope now you at least have some intuition to speak about PCA. What PCA does? TSNE tries to preserve the geometry. PCA tries to preserve the spread. Okay. And if you preserve the spread, again, I'm emphasizing on this, it is likely with less number of dimensions. Okay. Likely with less number of dimensions, you will be doing better at your task. When I say likely, it is not necessary. Okay. Less number of dimensions, that you will be better at your task. Okay. That you will perform better at your task. Better, equivalent, or almost similar at your task. It will not always help. Okay. Yeah. It is not always helpful. Okay. It is not always helpful. Yes.
Dimensions was very high. PCA will not help me on that case. So I supposed to use TSNE on that.
No. Even PCA can be, see again, the objective of TSNE is different. Objective of PCA is different. Both, even though both are dimensionality reduction techniques, TSNE, I'll just write it again. TSNE is used to gauge the complexity of the classifier. Okay. Okay. Gauge the complexity of the model. This is a pre-processing step. Okay. So with the help of TSNE, you can gauge the complexity of the model. Okay. With the help of PCA, you can get reduced features and then you do classification. Okay. Then you can do classification or regression on top of it. Okay. Do classification and regression on top of it. This is a pre-processing step. Okay. It's not, see, PCA should not be used to get the reduced features and use it for a classification purpose or a regression purpose. I'll repeat this. Even though I've shown it to you in the implementation, this was just to show you. Okay. It's used as a pre-processing step. Please remember this. It's used as a pre-processing step. Okay. To gauge the complexity of the model that you are going to pick. With PCA, you cannot gauge, but you can directly get the reduced features and do classification and regression on top of it. Evaluate the performance. If it is better, you go with it. Okay. If it is better, you go with it. Okay. If it helps, you keep, if it helps with reduced features, you keep it. Okay. Then keep it. Otherwise, see, please remember this. Every method has its limitations. PCA is a linear dimensionality reduction technique. Okay. PCA is a linear dimensionality reduction technique. I'll give you one example where this will not help. Okay. The importance is linear. It can only help when the projection data, when it is projected linearly onto a surface, then it helps like this. Okay. Do you tell me, okay, now see this. Do you think PCA will help? Okay, let's say this is how the data looks like. Okay. I'm giving you the labels just to give you an example. Okay, let's say this is how the data looks like. You are doing classification. Forget the labels for now. Okay. Forget the labels for now. The objective is that, okay, you have this data given to you. If you project it linearly onto a surface, where will X's be projected? Here, right? Or even if you do it along the dimension wherever it is maximizing. So if you project these points X's, okay, here, where will the triangles, where will the circles be projected? Circles will also be projected alongside, right? Yes or no?
Yes.
Do you think it will help? Do you think it will help? Will you be able to separate the data along this new dimension Z1? No, right? It is still very difficult. If it was originally difficult in X1 and X2, do you think Z1 helps? No, right? Same thing if you look at now this along dimension Z2, okay? Don't you see that it will still be a problem? Yes or no? It will still be a problem along this dimension Z2 also, right? So it is not always that PCA helps, okay? Keep that in mind. It's a linear dimensionality reduction technique, okay? It projects the data linearly. Now, that is where, like, SVM may be better in this case. If you think about it, what SVMs try to do, they can actually project this type of data onto a three-dimensional surface, okay? Onto a three-dimensional surface. So treat this like a bowl, okay? So treat this like a bowl. So this is like the upper surface, this is like the lower surface. So this is all your circles, and these are all your X's, okay? Now, if you view it, maybe say from the top, okay, don't you think that you get the same surface? The 2D projection of this data wouldn't be the same as this? Yes or no?
Yes.
Okay. So with SVMs, if you use, say, the polykernel, okay, if you use the polykernel, it can actually project the data from this to this. And then you can find a three-dimensional plane which can make it separable. So it is not always dimensionality reduction is helpful. Sometimes we have to take up the data to a higher dimension to make it separable. Okay. So, like, again, I'm emphasizing it depends on the data. You have to check and evaluate. See, currently the examples that I'm giving, they are in 2 or 3 dimensions, right? So you are able to visualize and see. Do you think you'll be able to visualize in more than 3 dimensions? Think again. What should be the answer to this? Would you be able to visualize it in more than 3 dimensions? The answer is no.
No.
So what should we do now? Then I can take help from what? TSNE. So TSNE is like a projection tool for us, which can give us an idea of what tool to use. So let's say if you try to project a 30-dimension data, which would probably is like concentric. So even in 30-dimensional projection from like 2 dimension or 3 dimension, it would still look like, so in 3 dimension, it will look like a enclosed sphere. In 2 dimension, it would look like a circle like this. If the data was like this in 30 dimensions also. Okay, if the data was like this in 30 dimensions also. So the projection of this in 2 dimensions would look like a circle. In 3 dimensions, concentric circles. In 3 dimensions, it would look like a sphere. That is why TSNE is like a pre-processing step. But if you try to do PCA on it, now you can understand, okay, in both the cases, it will not work. Okay, in both the cases, it will not work. Is this clear?
Yes.
Okay, all right. Okay, now let's see, okay, how much you guys have learned. So I'm going to share some questions with you guys. and probably we can discuss some of these questions. You try to answer these questions, see how much you have learned. These are somewhat challenging. So if you feel like, okay, this is going beyond, then I can discuss the solutions to these questions as well. Maybe in tomorrow's class, and I'll extend it also. So tomorrow would probably be my last class with you guys. Okay. So I'm going to share my screen, put up some questions, and then we can discuss these questions one by one. I'll share some projects with you as well. Let's see if the time permits today. I'll share some projects today itself. Okay, let me open up a set of questions which I have. Let's see. These are the questions that I typically ask, okay, in an interview. Initially, it may seem like, okay, they are easy, but trust me, as you go forward, I mean, it will be difficult. So let's try to interact and answer these questions one by one. What do you think are the different paradigms in ML? And you can think of, say, 2 general tasks under each paradigm. So what are the different paradigms? We have studied everything, by the way. What would you say if this question is posed to you? Or shall I give you the answers to each one of them, or do you want to take an attempt here? Can we keep it interactive, or shall I just give you the answers to each one of them? I don't have a solutions book for this, by the way. Do you want me to discuss these questions, or I mean, you can figure out the answers to them by using ChatGPT or Google? Okay, so what do you think are the paradigms? Let's discuss it quickly. Paradigms are supervised, and unsupervised. And in supervised, can you think of 2 tasks? Classification, regression. In unsupervised, can you think of 2 tasks? Clustering, market basket analysis, anomaly detection. Think more. Dimensionality reduction that we have done. Okay. So whatever task that you have studied, you can explain. Okay. If they ask you further, the interviewer asks you further, you explain. What is the difference between parameters and hyperparameters? Take an example and explain.
So hyperparameters are the attributes that we set to give the best model, and parameters are the features in the data set.
No, I mean, shouldn't say it like this. You're right for hyperparameters. So hyperparameters are entities that you manually tune.
Yes.
Okay, by providing us, you can say a list of values. Parameters are like, I mean, you give an example, say linear regression. So parameters will be the coefficients.
Okay.
The weights, the theta.
Theta 1, theta 2 is that we do.
Yes.
Okay.
Hyperparameters in linear regression, it's none. But if you think of ridge, what is the hyperparameter?
In ridge, it is the
lambda.
Lambda, yeah.
It's called as alpha in the implementation. Okay. Now, this is an important question. This is generally there to trick everyone. Now, please think about this. The question it is saying is, imagine you are given a data set, okay, and you train a regression model and you get these weights. Let's call these weights as W0, W1, WD. Okay, these are the weights that you get after training the model. Now, what is being said is, assume that your Y remains the same. Your output is not changing. But the feature values are multiplied by 2. What will happen to these weights? Can you comment on that? Think. So your Y values are kept unchanged, but all the feature values are now multiplied by 2. Do you think you can come up with a solution where these values will change? And what will these values change to? If you can answer this, you have truly understood linear regression. If not, then perhaps there is a lack in your understanding. Read the question again and think about it. I'll give you the answer to each one of these questions.
The weights will remain same if I multiply each feature with 2.
Okay, maybe I'll just again switch to the other device. It's difficult to keep on switching. But anyways, I'll switch to this other device and give you the, and probably show you okay, why they will change and what they will change to. Okay, can you see the screen, the other screen now?
No.
Okay, maybe it will come up in a 5 seconds. Can you see it now?
Yeah. No.
Yes.
Okay, it's coming up. Okay, all right, let's see this. Okay, so imagine I give you this data. Okay, this is X. So there are some features and the output is Y. Okay, you train a model. How many thetas will you get? D plus 1.
Yes.
So basically you get W0, W1, W2 up to WD. Okay. All right. Let's try to understand this. Okay. So can I say that once I obtain these weights or thetas, or you can call them as model parameters. Okay. If I give you the sample A1, A2 up to AD, if these weights are optimal, what do you think this W0 plus W1 A1 plus W2 A2 and so on till WD AD should be closer to?
Y1.
Y1, right? If these weights are optimal. Do you understand this?
Yes.
Okay. Now I am saying that you multiplied each of these values, each of the features by 2. So it becomes 2A1, 2A2 up to 2AD. So now this becomes 2A1, 2A2 up to 2AD. Okay. So what should W1 become to compensate? And you're not changing.
W1 divided by 2.
Yes, that was the answer. But what happens to W0? It doesn't
W0
change.
remains same.
Yes, that was the answer to this. Okay, so this level of understanding is what is needed. Okay, so this was, I said it's not, it's a challenging question, but not a trick question. Now, see, you came up with the answer, right? I did not. I just posed a question. Okay, so this level of understanding is needed for you to crack your interviews at good places. See, any company which is going to pay you 6 to 8 lakhs will probably hire you if you are, say, even decent in programming. Okay, but if you want to crack the big shots, then you need to have this level of an understanding. So this was the question. This was a question that I formulated. So these type of questions would be asked to you, and this is what I typically ask whenever I go and take an interview for these big companies. Okay, so I'll just switch to the questions back. Okay, I hope you can see the screen now. Okay, what do you think the answer to the next one is? So when you're doing L1 norm, you increase the value of lambda, the alpha. What do you think happens? So you're doing essentially lasso. So what happens? Yes, people. Anybody who remembers?
Increasing lambda, I'm increasing the penalty.
Yes, it means increasing the penalty.
So I'm moving I'm moving away from my best fit line.
Yes. You are tending towards underfitting, if you think about it. Okay, so if you tend towards underfitting, if you increase it too much, what happens? Do you remember it contributes to explicit feature selection?
Yes.
Coefficients will become 0.
More 0, yes.
Okay, so that is what you have to gauge. From this question. So you have to answer that. Most of the features will not play a role if it is increased too much. If it is increased to a fair extent, then some of the unimportant features will be going to 0. Does that make sense?
Yes.
That was the answer to this. Okay. This question is a little tricky. Can you use covariance to estimate the strength of relationship between two variables? Okay, which metric do you use to estimate the strength of linear relationship between two variables? Which metric do you use to figure out if two features are linearly correlated or not? Yes, people. Which metric do you think is used to figure out if two features are linearly related or not? Do you remember correlation? Correlation is a value between -1 to 1. Okay. Do you know the formula for covariance and correlation?
Covariance, yes. It's like
Xi minus Xi bar, Yi minus Y bar, right?
yes.
And we are doing the summation of it. There is a 1 by n outside. Okay, this is what it is. Okay, I'll just again These things are, see, again, you need to revise all these things. I'll just switch back to the original screen. So maybe what I'll do is I'll share these questions with you. Okay, if you guys search upon it, and then we can discuss the answers to them tomorrow if you are struggling with some of them. So tomorrow would be my last, what you can say is the session with you. Okay, so do spend some time in understanding them. Okay, and if you don't have any questions tomorrow, I'll just give you the projects, and then you can work on it like whenever it is convenient for you. Okay, they will not be Goovy's official projects, but they are the ones which I am giving from my side. Okay. So if you remember what correlation is, let me talk about first covariance. So covariance is given as, so it is the estimate of relationship of strength between two different variables. Okay, say A and B, or say X1 and X2. Okay, you can take any two variables, and this is the measure between two different variables, not the same. If it is the measure between the same variable, it is called as variance. Okay, so this is how it is given, like, so AI minus A bar, okay, into PI minus B bar, and there is a 1 by n outside. Okay, this is covariance. Okay, and correlation is, okay, correlation is this. Covariance divided by magnitude of A multiplied by magnitude of B. Okay, this is what makes it, sorry, this is not magnitude of A, this is standard. I just give me a sec. Okay, is this the magnitude or no, this is the standard deviation of A multiplied by standard deviation of B. Okay, so this is your correlation. Okay, this is your correlation. Now my question is this, you know that correlation is between -1 to 1. What do you think this covariance is between? What do you think covariance is between? Can you gauge like the range of covariance for any given example? Do you think it is bounded, first of all? That's the first thing. You think it is bounded? Okay, let's take an example like this. Okay, maybe say this is 1, 2, and 3, and this is say 5,000, 6,000, and say 100,000. What do you think covariance will come out to be? Will it be a value between 0 to 1, or will it be a value which would be high? What do you think? Any guesses? Do you think this value can be greater than 1? If it can be greater than 1, it can be infinity also, if you think about it. See, essentially, you are taking each value, subtracting it. So let's say this is A and this is B. Okay. So if you, what is the A bar here? 2. What is B bar? So it would be basically 6,500. Sorry, 10 is 16,000, 21,000. So it would be 11,500. Okay. This would be B bar. Okay. Sorry, no, not this. My bad. 21,500, 21,000 divided by 3. So 7,000 approx. 7,000. My bad. Okay. So if you do this, what do you get? 1 minus 2 into 5,000 minus 7,000. Okay. Plus 2 minus 2, which would be 0. So no need to do this. And then 3 minus 2 into 10,000 minus 7,000. Okay. What do you think this value is? Is it higher than 1 or smaller than 1? And you're doing 1 by n outside, 1 by 3 outside. What do you think this value is? It's a positive high value, right? Yes or no? See, this is -1. This is -2,000. Okay. This is +1. This is +3,000. Okay. It's a positive value, right? So it can go up to infinity. Now, what if I make these numbers as negative on the B side? It can go up to -infinity. Okay. So covariance is essentially dependent on the range of the features. Covariance is dependent on the range of the features. So it is not a good metric to find the strength of the linear relationship between the two variables. But correlation, whatever, so what you can do is try out this formula covariance, okay? Find sigma A, sigma B, divide that, okay? And you will see that for any range, it will squish the values between -1 to 1. So that is why correlation is used and not covariance. That was the answer to this. So correlation is nothing but covariance divided by the product of the standard deviations of the two variables. Okay. So this kind of clarity is needed to crack big interviews. So my job is not to discourage you. I'm just trying to help you with, okay, what is about to come next. See, for, you can say, for tier 2 companies, they will not ask in this detail, but if you really want to shine bright and maybe say excel in comparison to your peers, so you need to have this level of clarity. I'm going to share this questions with you, and what you can do is probably go through these questions, and whatever question that you can't answer, we will discuss it tomorrow. Okay, and I'll share some projects. So tomorrow would be my last class with you. Okay, I'll share just a second. Is there a way to share this, or shall I put it onto your drive folder? Because I can't see a way to, share something. I got it. Okay. So I'm sending it to everyone. I'll upload it to the drive folder also. Just a second. Okay. So I've put the questions in the chat window. You will have around 25-30 questions. So work on them, and then we will discuss these answers tomorrow. I'll stop here. If you have any questions, do let me know. Okay, we'll discuss the projects and some data analysis tasks so that you can practice as well for your upcoming interviews. Okay, I'll keep them all in the same folder. So whatever you want to discuss, right, bring it tomorrow. If you think we need one more class, we will take one more class also. Like after, so I think we have sessions till Thursday, right? So if you think there is a need for Thursday session, I'll take the Thursday session also. But if we can finish it tomorrow, that would be great. Okay, I will also have a leave for one day. Okay, and you guys will also be done by then. Okay, but if there is no response from your side, okay, we will not have Thursday session. So I'm only going to come tomorrow. If there is no response tomorrow, we will not have the following session. All right, guys, I'll upload this to your OneDrive folder. If you have anything to say, go ahead. Or anything to ask. Yes, people, anyone? All I can say is the best of luck. Okay, if you need any assistance, please reach out to me if you're applying to any company, especially say the top tier ones. I have a lot of friends, so I can refer you in case. So please reach out to me once you have applied, so I can expedite the process. Okay, I will not be helping in those cases where you ask me to find jobs for you. I cannot do that. Okay, once you find a relevant opening, if you have applied, then you reach out to me. I'll try to expedite the process for you. Okay, so that way I can help. But if you say that, okay, I'm looking for jobs, please help me, I am not very receptive to that. Okay, because for me to create a specific job for you without assessing you and all that, that is troublesome for me because that will reflect on my name. Okay, so I will not take that risk. I hope you get my point. Okay, because see, in that case, you'll be representing me. Okay, and since we have not met, it's all online. Okay, all I can say is that you were interactive or not during the sessions. right? I hope you get the idea. Okay. If it was a face-to-face class, I would have recommended you as well. But this way I can, I mean, because it's online, I can only help with expediting the process for you. Okay. I would be more than glad to. Okay, but don't expect me to especially search for you. Okay. So I have my own commitments and you have yours. I understand that. And you should, I hope you get my point. Okay. I don't want to be rude.
Yeah, totally.
Okay. No, because
Yeah.
some students have reached out to me saying that, okay, sir, could you please help with this? It becomes very troublesome. Okay. It becomes very troublesome. Okay. So I'll stop here. Any other questions I can help with? If you need any assistance, please speak your mind. Yeah.
So Sanatan, like basically, like I'm aiming at like data analyst roles.
Mhm.
To start off, like first, let me just get the feel of the waters and how deep the waters are, and then maybe like once I get into the industry, and then I will start aiming for the next level roles. That's how I am planning.
That's how you should plan also. I mean, not just data analysts, you dive into data science roles also. You also dive into, I would say, SQL engineer roles. You can also target what I say is no SQL developer roles. Okay. But before that, like if you're targeting for these niche jobs, maybe say a Python developer also, if you are fairly good in Python also. So there are many branches open for you now, not just data science. So wherever you can kind of get into, okay, do that. Okay, and with the time, obviously, you will become better. So maybe try switching after every 3 or 4 months or after every 6 months. So if you find a better opportunity, have something in your hand, okay, instead of maybe regretting it later. Okay, I had this chance, but I kind of skipped it because I wanted to earn more or I wanted to have a better package. Okay, so that way you try to get something in your hand first. Do it alongside as a better opportunity comes along. I mean, move towards it. I mean, move to it, and you can always make a transition, right? So
Yeah,
don't
transition, yes.
neglect any opportunity. That's what I'm saying. Okay. Okay. I know that you have a sense of worth. Everybody does. Okay. Even I do. If somebody offers me a package which is not as per my expectations, I would probably decline it at the very first moment. But I'm saying that if some opportunity comes along your way, don't decline that, accept it. Okay. As the time comes, you move to a better position. Okay. So have something in your hand before, I mean, making a call of declining or neglecting something. Okay. Have something in your hand first. That's what I'm trying to, suggest here. So don't take my words in a wrong way. I'm just trying to tell you how the market is like. So it needs a lot of data scientists. There is a lot of what we say competition going on. And when there is a lot of competition, the salary is paid well. And sometimes it is not paid well because when the demand is more, the influx is also more. Okay. It takes time to figure that job out, which pays you well. So sometimes these jobs may not come along your way directly. Okay, so wherever you can get in, you fit in first, and then you explore. Because once some name is associated with you, the others will also try to take you up. Okay, instead of rather waiting. Okay, no, I deserve say company XYZ, at least that much. So don't do that. That's just my perspective.
Yeah.
So Sanatan, in the ERP companies, we have like CMM level 1, CMM level 2, level 3, like that. So even in this field, like, do you have companies related like that?
Okay, I'll tell you. See, I don't want to discourage anyone. I have always targeted what I say is tier 1 companies. Okay, from my side. Okay, so I can talk about my experience, what it has been. I have also faced a lot of rejections. I've worked in the best companies. Now I prefer doing freelancing for them or consultancy for them. So my journey has not been like very smooth. I think it's the same for everyone. Initially, it is a little difficult, but then when you transition, right, offers come along your way. I can tell you this much. See, it's not, I don't want to brag, but every week or every 2 weeks, I get 1 or 2 offers. Okay. So once you are in a position, people are they are trying to search, HRs, they are trying to search. So it will happen to you as well. Okay. So target, ensure that you have a good target. Start with something. See, I also started with HCL. Then I moved to Siemens. Then I moved to Amazon, and then I moved to Intel. Okay. So your progression should also be, if you can get into a top tier company, why not? Okay. And then the progression should be among the top tiers, not go down. But so when you start your journey, start from whatever you can get. Okay. Because it is difficult to get into first. So once you get into,
totally
Thing is smooth.
mindset, like my mindset is like I don't know why, but I used to take interviews in my company and all those, but now it's feeling really like I was literally getting afraid of facing an interview. I hope you can
no, you can definitely crack it. Okay. So don't worry too much. Okay. Just be prepared when you go for an interview. Don't get disheartened when you don't crack one. I'll tell you about my, what we say is like olden days. When I started this journey, I kind of failed in maybe say 10 plus interviews. Okay. So I come also from a private college. When I started my journey, then I moved to a better college like NITs, then I moved to IITs. So the journey is, yes, obviously progressive, and that would be the case with you as well. Okay, so it will actually evolve over time, and there is no what we say is like nectar or a way through which, or maybe say some magic potion which someone can feed you. Okay, and you become the best. It comes with practice only. It comes with time. Okay, you will definitely be able. I can assure you that if you have done at least my ML part correctly, okay, have given dedicated hours to it, at least a data science job you would be able to crack within your first 5 or 10 interviews. Okay, for sure. If you have done at least my ML part correctly. Okay, you know, you can see yourself in the mirror. Probably, if you have attended all of my classes, you would be able to retain a lot as well. Okay, so even attending my classes would have been. I'm not trying to brag again, but hopefully,
totally.
hopefully,
I have to
when you
give
clear your
my full attention towards what I'm trying to do. That's what, right? Because
let's just be hopeful. Okay, let's be hopeful. Okay, this will reflect in your success as well. Okay.
I'll surely drop an email to you one day. That
Okay. I look forward to that. Okay. All right, guys, I'll stop here. We'll meet tomorrow. I'll give you some projects also. And we'll upload this to your Drive folder. We will do some data analysis tasks. Okay. If you feel like you need a session on data analytics, how to extract insights, we'll do some of these things. Maybe I'll give you a problem statement. You try to do it for say half an hour. If you get stuck, I'll show you live, okay, how to do that. I think this is more than sufficient to crack an let's say entry level or 1 or 2 year level job. Obviously, for high paying jobs, you have to get into a company, understand the infra, understand I would say the pipeline architectures more. You have to be familiar with Spark because you'll be working with Spark clusters. So I think that eventually will fall into place, but you have to get started somewhere. Okay, you have to start. Okay, don't think any decision would be a bad decision. Just and if it's a bad decision, you can always redo it or transition. Okay.
Yeah. So we have to put an initiative for anything.
Yes, and again, I'll emphasize on this. Even if you get say a 5 lakhs salary or say 4.5 or 3.5, okay, as a fresher, okay, you get into that. If you are an experienced programmer, then I say don't compromise with your existing salary. Always look for slightly better one. Okay, even if you get say maybe half lakhs less, then you can transition into it, and then things will eventually fall into place. Okay. See, if you're not getting a hike, okay, don't get too tensed because you have just made a transition, okay, from your company A to company B. I assure you that within 1 year, you will at least see 50 to 100% hike, even more. Okay.
And what
Because,
about in case of career gap? Should we expect or not?
I think you will be definitely asked a question on that. Okay. People are understanding. So it's not going to be a bottleneck unless your skills shine. I'll probably say it this way. Okay. See, if you are not skilled, a career gap would be just what they would cherry pick to kind of like push you off.
Yes.
Okay, so career gap is something which people just highlight. Okay, if you are skilled enough, nobody cares. Okay, that is my opinion. Okay, maybe like some other people have a different opinion. I don't know. But as far as I have interviewed people, I have met a lot of people with career gaps, especially women. Okay. However, I have always felt that women were more deserving than men. Okay, so not trying to kind of butter you up, but career gap is not a what we say is a hurdle. Okay, as long as you are skilled.
Okay.
All right, I'll stop here. Let's meet tomorrow.
Chantan,
Yes.
last one question. Like,
Yes.
in my case, I'm just trying to get in as a fresher, like in data analyst or a data science role. So, like, I'm expecting around 6 to 7. If I'm getting that range, I'm enough with it because I'm not looking.
It will be difficult, Nish. It will be difficult.
Okay.
Okay,
So
it's
6
very
to 7
difficult. The very
will
first
be-
job would be difficult for if you're expecting 6 to 7. But
Okay.
5.5 you can crack. Okay, 5.5 you can crack.
Current was little bit.
Again, see, if the company takes into account your current salary, obviously they will not demote you so much. So if you are working at a better role, don't compromise more than let's say 0.5 lakhs.
Okay.
Okay. So whatever your current salary is, I don't need to know that, but don't go below 0.5 lakhs. Okay. I believe that most companies would offer you as much or slightly better, even if you are applying for a fresher role. No company is that inconsiderate. Okay, or they will reject you at that very moment if they can't pay you. Because the first thing that they ask is how much your CTC is there, right? Like in hand.
Yeah. Okay.
Okay, so they will reject you at that very moment if they can't pay you.
Yeah,
Okay.
please, I totally understand that I'm transitioning into a new field, but at the same time, I can't, when it comes to this financial stuff, I can't come down with.
I agree. You shouldn't, right? That's why I said at least the same, just 0.5 lakhs less. Okay.
Okay.
That's why I said just 0.5 lakhs. Don't go any less than that.
Any less?
No. You shouldn't. Okay, you shouldn't.
Sure.
If you are a beginner, then I said yes, you can target say 4.5 also. Okay, even 3.5 lakh salary is not appropriate for nowadays. You're not just relying on your own survival, right? Others also probably depend on you. So, okay, so don't under compromise as well.
Sure.
Okay, all right.
Yeah, one day I'll meet you.
Bye everyone. Take care.
Bye.